Hello everyone, I am glad that you could join today for this session. My name is Anca Iordache and I am a software engineer at Docker, where I am working on developer tools for containerized applications. Today we are going to talk about best practices for developing Python projects in containerized environments. In particular, we are going to see how to use Docker Compose and other Docker tools to speed up our development process. Developing Python projects in local environments has its own challenges. As we well know, starting a project is sometimes time-consuming, as we need to manage versions and set up dependencies and configurations for it. The classical way to do this was to install all project requirements directly in our local environment and then focus on writing the actual code. But having several projects in progress in the same environment may become quite a problem, as we may get into configuration or dependency conflicts. One way to avoid these problems is to create isolated dev environments for each project. Using containers and Docker Compose is among the best ways to manage such isolated environments. So for this, we are going to tackle two main points during this presentation. First is how can we quickly spin up a container-based dev environment for a Python project. And second, once we have this isolated dev environment, how can we update and debug the Python code? So we address these matters in two main parts, and for each we analyze several aspects. First, for bootstrapping a Python project, we'll discuss how to split its different functionalities in isolated components or services, and how to organize project files and data to make this split more obvious. Then we'll see how to containerize its components or services and wire them together. Here is also where we are going to cover some best practices for Docker files and Compose files. In the second part, we go through the development cycle of a project and discuss in more details how can we apply code updates and debug failures in a containerized Python service. This is also what we are going to quickly demo at the end of the presentations. So let's start with the bootstrap phase. Before starting with the actual code, we need to make sure we have a minimal set of tools installed, such that we can easily follow the steps we'll discuss next, or at least the basic knowledge about their role or purposes. For Mac and Windows, we need to install and run Docker Desktop to be able to run Docker containers on these systems. Docker Desktop will come packaged with Docker Compose, so there is no need to handle anything else separately. And of course, we also need to have an IDE with Python support. On Linux, we need to install the Docker Engine and Docker Compose tool according to the distro used. So with these requirements covered, let's start with the project. We take as an example an application for which we separate its functionality in three tiers. This is a pretty common architecture for multi-service applications. So our application is going to be composed of a UI tier, which will run on an Nginx service, a logic tier implemented as a Flask service, and as we may need to store some data, we also require the data tier, for which we'll use a MySQL database. The reason for this separation is that by splitting an application into tiers, we can easily modify or add new ones without having to rework the entire project. So once we have this clear, let's start organizing our project. We'll start with the development of a Python service, and we'll see how to add the other components later. So a good way to structure the project files is to have a per service directory. So we create a directory called app for our Flask service in this case. We then write a simple server that returns a hello message. And aside from the Python code, we have to create also a file with the required dependencies for our service. In this case, we need to install the Flask framework. Now, in order to run this simple Python application, we need a Python interpreter and, of course, to install the dependencies. So we could do this in a classical way by installing the Python interpreter and the dependency on our local environment. But this means we would pollute our standard dev environment, and we want to avoid this. So using containers to run it, however, would help us to do this easily. Therefore, let's have a look how can we easily containerize it. So to do this, we need to understand how do we get from the Python source code to the running container. The solution is to package our application as a Docker image, and then we can get our container with a simple Docker run. But how do we generate a Docker image in our case? Well, the only thing we need to do is create a Dockerfile which contains the instruction needed to build the image. The Dockerfile is then processed by a Docker builder, which will generate the Docker image. Then, doing a Docker run on that image, we'll get a container created and launched by executing that Python service. Let's have a look at the Dockerfile for our simple Python server. So just a reminder here that we'll cover mostly best practices that speed up the development time. If anyone interested in production-focused best practices, please check the blog post at the link on the bottom. That will cover this topic in more details. So to start with, this is how our Dockerfile looks like for our Hello World server. As you can observe, a Dockerfile is a text file containing instructions for assembling a Docker image. Each instruction or command is processed by the builder, and an image layer is generated from it. Let's go through some of this instruction now. So the first instruction will actually specify the base image on which we add new layers from our application. In this case, we decided to use a Python 3.8 image that should contain all the necessary standard tools inside such that we can easily run our Python program. We can change this base image according to what we are looking to do. For example, if we seek to generate a small image, we'd better check the Alpine tagged image that should contain a minimal install for Python. For other particular tags, better check the Docker Hub image page to find which one fits the case we are looking for. We discuss next the copy and run instructions. As we mentioned before, for each instruction in the Dockerfile, the Docker builder generates an image layer. What we forgot to mention is that the builder also caches the image layers that it generates. This means that if we make a change in one particular step, all the following layers are going to be generated again. The copy and run instructions are some commands that usually generate changes and, as a consequence, invalidate the cached layer. So we need to make sure we use them in an efficient way. For this particular case, we can see that we copy the dependencies files and then the source code. This is because the application dependencies do not change that frequently during development time, so we choose to install them before copying the source files that usually change frequently. It is highly recommended to add instructions for layers that do not update frequently before the ones that get frequent updates. This is in order to benefit from the cache mechanism, and this will speed up the build time for our application image. Finally, we copy the source files and specify the command to run the Flask server, and this will be the last image layer. So once we finished writing the Docker files, let's see how to run our Python server in the container. So we go in the project directory or the app directory, and we run the docker build command with the path to the Docker file. Next, we check the image with the tag specified in the build command is in the local image store, and then we can start a container with Docker run with the generated image. This being done, we now containerized our Hello World server. So let's see how to add a new component to the project and how to wire it to our Python service. We're going to add a database service to the project, and for this we update our Python code with a database connection. This requires also to import the library needed to connect to a MySQL database and add it to the dependencies files. Once we've done that, we need to rebuild our Python application and run the container. But at this point, we need to start a database instance too. So how can we manage this in an efficient way? Well, here is where Docker Compose offers a very easy way of coordinating containers and spinning up and taking down services in our local environment. For this, all we need to do is write a compose file containing the configuration for our project services. Once we have it, we can get the project running with a single command. So let's see what is the structure of the compose file and how can we manage the DB service with it. This is the sample file for our Python service and the database. As you can see, we define a list of services, and in the DB section we specify the base image directly, as we don't have any particular configuration to apply for it. Meanwhile, for the Python service, it is going to have the image built from the Dockerfile. According to where we get the service image, we can either set the build or the image field in the compose file. If the build field is set, make sure it is a path with a Dockerfile inside. To initialize the database, we can pass environment variables with the DB name and password, while for our Python service, we map the container port to the local host in order to be able to access it as in the usual way. Now, let's see how to deploy our two-service project with Docker Compose. All we need to do now is to go to the project directory where we place the Docker Compose file and run Docker Compose up. Docker Compose is going to take care of pulling the MySQL image from Docker Hub and then launching the DB container, while for our Python service it is building the image locally and then running the container from the built image. All this is triggered with only one command. So let's see now how to add the third and the last component to our project, the web UI service. As we did before, we create a dedicated folder as we have specific files for it, and we add the code and the Docker file to build its Docker image. So to be able to access it, as it is the front end for our project, we map the port 80 to localhost in the compose file. With a simple compose up command now, we can spin up the containers for all the three services of our project. But let's analyze the setup a little bit and see how can we optimize it by following best practices for writing compose files. When we have several containers, we need to control how to wire them together. So we need to keep in mind that as we do not set any network in the compose file, all our containers will end up in the same default network. This may not be a good thing if we want that only our Python service to be able to reach the database. To address this issue, in the compose file we can actually define separate networks for each pair of components. In this case, the web service won't be able to access the DB. To have a more secured setup for the containers, as a good practice, we recommend to be very careful about network isolation. So other ways to improve our project setup are the following. If we want to persist DB data between different containers or runs, it is recommended to use named volumes to have them persisted. We can explicitly remove the named volumes on Docker Compose down if we want this. Another point is that to increase password safety, it is recommended to use Docker secrets to store it and provide them to the services that need it. So now that we have a well-defined compose file for our project and we can easily run with Docker Compose, let's start the second part of our presentation. So we'll focus now on the dev inner loop, and mostly we will analyze how to speed up project updates and how to debug Python code running in containers. In general, our containerized development cycle consists of coding, building, running, and debugging. For the building and running phase, most of the time we actually have to wait. So ideally we want these phases to go pretty quick such that we focus on coding and debugging. Let's see how can we optimize the build phase for Python development, especially since it is interpreted and not compiled. We can analyze how to avoid this step during development. So as the build phase corresponds to image build time, when we change the Python source code, the image needs to be rebuilt in order to get that change in the container when it is being launched. So we can apply these code changes without having to build the actual image. We can do this simply by mounting the local source code directory to its path in the container. For our particular project, we have to mount to app src to src path in the container. So with this, we can skip the image build and just restart the container to reload the Python process. The last point we analyze is how can we debug a containerized Python service. So generally, we need to set up a remote debugger in the container and to expose a port for communicating with it. Then we need to set up our IDE to connect to it, and here it should be a very similar experience to when we run locally. We can do this for our Python service in the following way. We need to import a debugger package in the source code and then update the dependency files to get it installed. And we need to expose the debugger port in the compose file and then set up the IDE with the debugger with it and the source code path. Remember that for changes we make in the compose file, we need to run a compose down command to remove the current container setup and then run a docker compose up to redeploy with the new configurations from the compose file. So to end this talk, we are going to exercise quickly each step we discussed about updating and debugging containerized code. Hopefully all this should make the entire Python dev experience quicker and better. We now are going to exercise what we discussed during the presentation. Basically, we set up a Python project and we see how to do updates and debug the Python code running in containers. For this, I'm running on a Windows Home environment where I installed Docker Desktop running with a WSL2 backend. As for the IDE, I am going to use Visual Studio Code for this demo. To quickly spin up the project, I downloaded an Nginx Flask MySQL sample from the Awesome Compose GitHub repository that has a similar tiers to what we want. I updated it to match the naming and the structure of what we discussed during the presentation. So this is our updated project. Let's check now the files. We start with the compose file and we see that it follows the best practices for service setup. We can see the network isolation, the use of Docker volumes to persist DB data, and also the use of Docker secrets in order to avoid having the DB password in plain text in the compose file. Also, to avoid rebuilding the image for the Python service each time we update the code, we mount the source code of the Python service, as we mentioned before, to the container. We also map a port of the Python container to the local host. We are going to use this later during debugging. So let's have a look now at the Python application. It is a simple Flask server implementing a DB connection and two API methods. The hello one will return a hello message, while the list block will return a list with block titles that are being retrieved from the database. It is important to notice that we have set the debug parameter of the Flask server on true. With this, the Flask server will watch for any code change and trigger a process reload in case it detects one. It will also provide a helpful debugger if things go wrong. Now let's launch our application and see how it looks like. For this, I'm going to run the Docker Compose build just to make sure that the images reflect the current state of our project. Now I'm going to run Docker Compose up in detached mode to deploy our application. And I'm going now to check. We can see also the Docker desktop dashboard and how the containers are up and running, and we can check the web service, and which is providing the user interface for our project. As you can see, we have a simple interface that we can use to query the Flask server. So we can do it. We can query the, let's say, the hello method with just by default we get the hello message returned. We can also query the blogs path like this. So as you see, we get the list with the blog titles. And I'm going to place that window here so that it is easier to check on several fronts what is happening. We can check the logs from our Flask server, as they may offer some useful information. As you can see, the Flask server started in debugging mode, and we can also see log information from the two queries we have run before. And as we mentioned, the Flask server is gonna watch for any code change and reload the process in case it detects one. Now let's see this. So I'll open the Visual Studio Code and place it in parallel just to make code changes and see the change going into the container. So let's assume we update the hello message and change it to hello from Docker. Once we have saved this file, let's watch the logs of the Flask server that will notify the process reload. So we save the file, and as you can see, it has detected the change in our source code and it has reloaded the process. So now if we query again the root path, we should get the hello from Docker message. So this is the update was applied right away. So this is a very simple way to handle code updates and debugging. Basically, if we make a mistake, let's say a syntax error, and we'll get this right away. And it's pretty easy to do this. But in the case where we want to have an interactive debugging session within our VS Code IDE, we want to place some breakpoints, for example, such that we can inspect the content of certain variables at runtime. To do this, we need to use a remote debugger that easily integrates with VS Code. So I'm going to use for this case the debugger package called ptvsd. So I'm going to modify now the files and enable this remote debugger. So but first let's stop our project instance, as it will detect the changes we do in the files and complain about errors. So we'll run a docker compose down. Now we'll import the debugger package and we set a port to which we can connect to it. And we also need to add it to the dependency files to get it installed in the Python container. So we save the files, but we need to remember to turn off the debug mode in Flask, as it may conflict with this debugger. Yeah, we need to notice So the port that the debugger process is going to listen to is the one that we have mapped in the Docker Compose file to the local host. So now we need to set up our VS Code to connect to this remote debugger. For that, we need to create a configuration of remote attach type, as we'll have the port mapped on the local host. So we'll connect to local host with this port, and we should not forget to set up the local path to our source code, which in our case is src, and also the path in the container of the source code, so which is /src. We save this configuration and we are almost ready to run in debugging mode in the IDE. But we need first to restart our project. Remember that we have removed the containers. So as we updated the dependency files, we need to run again a Docker Compose build to generate the latest images. Now that the images are up to date, we need to deploy again our project. We'll see our containers running, okay, and now we can try to place a breakpoint in one of our methods, and we are going to trigger this method call with a very simple query from the front end. We have updated it, so we refresh. So for this one we need to call blocks, but we shouldn't forget to start debugging, and we have to do it with the configuration file that we have previously set. As you can see, we have connected to our remote debugger. So now we can actually trigger the API call where we'll reach our breakpoint. So as you can see, we've reached the breakpoint, and now we can inspect the value of our objects. So we can see result, the list of block titles. We can check also the connection object with all the data about the DB connection and so on. So this is how we can update and debug Python code running in containers. I hope that what we discussed may be useful for you, and that may help to improve the Python development experience. Thank you very much for attending, and I hope you enjoy DockerCon.